Hi, Tom the Professor here. It's time for another problem. Let's get started. Well, the sun has finally come out and is melting the snow from our recent blizzard. So while I was looking through the textbook, I found a problem that dealt with ice and snow and a car sliding. What would be more appropriate? This particular problem comes from the chapter dealing with forces and Newton's laws. So I'm going to solve the problem using just that information the first time, and then we'll see where we get from there. We'll start with what do we know? Mass of the car is 2,500 kilograms. It has an initial speed of 14 meters per second, and it stops in a distance of 25 meters. Right? If the car comes to a stop from its initial speed, that means that the car must accelerate. Now, in physics, we call it an acceleration, positive or negative, depending on whether it's speeding up or slowing down. But we use acceleration for the same term. So, now, if there is an acceleration, that must also mean there is a net force, and that force has to be in the same direction as the acceleration, which means towards the back of the car. What we need to find in this problem is what's the coefficient of friction between your tires and road. Yes, it is an icy surface, but friction is still important when you're dealing with driving a car. Otherwise, your car will just continue in a straight line at a constant speed until it hits something, right? That's Newton's first law. So friction is going to be important to keeping your car on the road. We calculate, so when we go to the possible solution, we're going to calculate the friction that stops the car because that's where the coefficient resides. That's the equation it resides in. The friction is given by the coefficient of friction times the size of the normal force. There are two things in this equation we don't know. We don't know the frictional force yet, and we don't know the normal force yet, and we're looking for the third one, so this doesn't seem to be a very good start. Let's see if we can figure out what either the friction is and the normal force is so that we can calculate this coefficient. Now we first off define the normal force to be a force perpendicular to a surface. So what the surface we're talking about here is the flat level road that the car is traveling along. So the normal force will be pointed straight up perpendicular to that. If we were driving up a hill, the normal force would still be perpendicular to that hill surface. And that doesn't matter the steepness of the hill. The force, the normal force is always perpendicular to that surface. Now, since we're dealing with forces and the normal force we want to find, let's take a look at a free body diagram. We've got our car driving along the road. We've already talked about the frictional force pulling towards the back of the car, which is going to be our stopping force. I'll put the acceleration here as well just to remind us that it is slowing down, so the acceleration is also towards the back of the car. And then we look at what other forces are acting on the car. Well, the car has mass, and it's on the surface of the earth, so that means it also has weight. We can calculate that weight pretty easily. If the car is also sitting on a road, that means the road has to be pushing upward with the normal force, right? So that's all the forces acting on the car. Right now we don't know any of those, but we should be able to work through what each of those is. In order to get an idea of what the normal force is, let's take a look at the forces that are acting up and down. In most of these Newton's law problems, you can split up the problem into pieces so that you're just dealing with one direction, up, down, or you're dealing with left and right, or you're dealing with forward and backward. Right? Now, we do know what the acceleration is up or down. It has to be 0. Why does it have to be 0? That's an excellent question. I'm glad you asked. The net force has to be 0, otherwise the car will, the acceleration has to be 0, otherwise the car will leave the surface and go floating off into space, or it will dig itself into the ground, and we don't want either of those possibilities to happen. So we'll set up the acceleration up or down is 0. If the acceleration is 0, according to Newton's second law, then the net force also has to be 0. So let's take a look at Newton's. So that gives us Newton's first law, actually. So we have the normal force pulling up, and we'll subtract off the weight because it's pulling in the opposite direction. And when we combine those two, we have to get 0 net force. So rearranging the equation, we have the normal force is equal to the weight, and we calculate the weight of an object by taking its mass times the acceleration due to gravity. The mass we have, the acceleration due to gravity, is a constant, so let's throw those numbers in there, and we get a value for the normal force of 24,500 newtons. That will go right into our friction equation in for the normal force. So I'll list it there so I don't lose it, and we'll come back to it after we see if we can find the frictional force next. Now the car slows down to a stop, which means it is going to accelerate, which means the net force is no longer 0 in that direction. If it's not 0, then we'll use Newton's second law because the car is going to accelerate. So the net force is the mass of the car times its acceleration. The force being applied here for our net force is friction, which we don't know. We want to find out so that we can put it in our friction equation. The mass we do know, and the acceleration, of course, we have no idea what that is yet in this problem. We should probably look into finding what that acceleration is. Then we'll get the frictional force, and then we'll head back and we'll be able to calculate the coefficient of friction. You see the path we're following yet? Okay, hopefully it will all make sense in just a minute here. So let's see here. Let's go back to the problem and remind ourselves. It's good to look back, just to make sure we didn't miss anything. We've used the mass of the car so far. When we calculate the acceleration, remember acceleration depends on speed. Normally the acceleration equation also depends on time, which is not given to us in this problem, how long it takes for the car to stop. But we are given a stopping distance, and if we really wanted to, we could calculate the amount of time it takes to stop. I don't really want to. Okay, so that's where we are there. So the speed is changing over a distance and over a time. Okay, rather than using the distance equation to calculate the time, which you can do, and the acceleration equation to calculate the acceleration then with the change in velocity, I'm going to go to this other kinematic equation. Normally when I'm teaching course and we're doing the kinematic equations, I come up with 4 equations. The distance equation, the acceleration equation, where it's the change in velocity over time, the velocity equation, which is the acceleration equation solved for velocity, and then this final equation, which actually comes from energy, but you can get it by taking the acceleration equation and substituting it into the distance equation, and out pops this fancy equation, where the final speed squared is equal to the initial speed squared plus twice the acceleration times the distance over which that speed is changing. That sounds like a good equation to use because the initial speed, the final speed, it comes to a stop. It's 0. I can zero that one out. The initial speed is given to us. The acceleration we don't know, but we want to know that acceleration so that we can put it back in our last equation. And the distance over which the speed is changing is the stopping distance. So we have that value. So let's take this equation. We'll solve for the acceleration because that's the only thing we don't know in this equation. Plug in the 14 meters per second, divide by twice the distance, and we get an acceleration of negative 3.92 meters per second each second. Now, this negative sign just means that the car is slowing down. We already know the direction of the acceleration from the pictures that we talked about when the car is slowing down. So in later steps, I'm just going to drop that minus sign because I'm just looking for the size of the forces, not necessarily their direction. All right, so let's stick that back in for our acceleration so that we can calculate the frictional force. The mass of the car, again, 2,500 kilograms. We'll stick in the acceleration. Again, I'm dropping the minus sign because I'm only interested in the size of the force. And that gives us a frictional force of 9,800 newtons. This we can stick into our friction equation then. We have everything we need. And we have, so friction is 9,800 newtons. The normal force, 24,500 newtons. And when you divide the two, that gives you the coefficient of friction of 0.4, which is the answer we're looking for. So let's collect all that information in our nice template. Starting with what do we know? What do we need to find? We start a possible solution by looking at the friction equation, and you see here F equals U times N. Fun. It's a fun equation. That's the way I remember it. We'll solve that for you. We need to find the frictional force. We need to find the normal force. We pop over to the other side. The normal force is equal to the weight, so that comes out pretty sweet. In order to find the frictional force, we're going to use Newton's second law, except we don't know the acceleration. So we got to step back, find the acceleration using this fancy velocity squared equation. Plugging all those numbers in then gives us the answer we're looking for. That's a lot of extra work, it turns out. But in the forces chapter, that is the way you have to go, because at that point in the book, all you have is the kinematic equations and Newton's laws to work with. Now, there is a slicker way to do this problem, but it doesn't come up until some of the later chapters when we talk about energy. If you think back to the last episode, we had a force acting over a distance to stop the Atlas stone as it impacted with the ground. The same sort of thing is going on here, so we should be able to use the same ideas to solve this problem as well. And it does turn out to be a lot slicker, a lot faster. So let's step back and do a second possible solution here. And what we have is the friction does work to stop the car. That's the big idea here. So if the friction is doing work, we should be able to use the work energy theorem in order to calculate the force directly, the force of friction directly. So let's put it in the equation here. The force times the distance over which the force is being applied is equal to the change in kinetic energy of the object. Now, the frictional force is the force. The distance is 25 meters, and that's going to equal a change in kinetic energy. Well, the final kinetic energy is 0 because the car comes to a stop. So that speed goes to 0. You square that, it's still 0. Multiply by the mass, it's still 0. Multiply by half, it's still 0. So that's where we get that 0 from. And then the initial kinetic energy is going to be half the mass of the car times the initial speed. So I'll plug those numbers in. And when we do that, we get a frictional force of 9,800 newtons. That's a lot faster than the other way to do this problem. So let's also write that one down in a nice template here. So the only thing that's changed here is I've got rid of everything after we found the normal force. We still calculate the normal force the same way as we did the first time. But in order to calculate the frictional force, I can use the work energy theorem in order to calculate that value. And then that gives us the same answer at the end. Isn't that much slicker? I kind of like those kind of problems. So that's the end of this episode. Make sure you like and subscribe to help support the channel. If you want to get a message to me, hit me up on the social medias. The link's on the screen there. Also, check out the blog, tomteacheспhysics.com, where I do a lot of other writings on physics and teaching and other things like that. There's also new merch for that. So go and check out the merch. Help support the channel. Help me make more of these videos. And thank you for joining me. I will see you next time.